Okay, welcome students to this next session on industrial metallurgy. We will continue our discussion on the iron carbon systems. This is session number 39. And as you remember, in the last session, we had started our discussion on the invariant reactions which happen on the iron cementite equilibrium diagram. There are three reactions. We have already discussed in detail the peritectic reaction. The other two reactions are the eutectic reaction and the eutectoid reaction, which we'll take up in detail in this particular session. Again, for your reference, I have shown here the iron cementite equilibrium diagram. Now it is this region where the eutectic reaction takes place, and it is this region where the eutectoid reaction takes place. So we will be more concerned about this region in the initial part of this session. Okay, here again, I have shown that A, B, C, D is the liquidus line, A, E, F, G, C, H is your solidus line for this diagram. And there are three important points: the peritectic point, the eutectic point, and the eutectoid point. Students, this is the eutectic reaction. We have discussed it several times now. Specifically, if we talk about iron carbon systems, when an iron carbon system is being cooled and it reaches the eutectic temperature of 1147 degrees centigrade, if this phase is present in an iron carbon alloy of this composition, then this entire liquid solution of iron and carbon via the eutectic reaction will transform to two new solids, one being austenite of maximum carbon solubility, that is 2.11 percentage carbon, and the other cementite, which is always of 6.67 percentage carbon. They are nearly formed through the eutectic reaction in the weight ratio of 1:1. And this mixture of eutectic austenite and eutectic cementite is referred to as the eutectic mixture called lead burite. Okay, students. So now, as I discussed with you during the peritectic reaction, there are a couple of questions which when one can ask you with regards to eutectic reaction. The first question would be that which of the iron carbon alloys will actually show this reaction. The answer is that any iron carbon alloy which on being cooled and reaching the eutectic temperature 1147 has got liquid solution of this composition in it will show the eutectic reaction. Now, if you look at the iron cementite diagram, you'll see that this condition is met only by cast irons. So every cast iron, any iron carbon alloy with 2.11 percentage carbon till 6.67 percentage carbon, when it reaches 1147, it would always have liquid solution in it, and that liquid solution would always be of eutectic composition 4.33 percentage carbon. So that means that every cast iron will undergo this reaction during cooling and also during heating. But none of the steels, you see iron carbon alloys till 2.11 percentage carbon are called steels. And now if you look at any of the steels at 1147, they just have austenite in them. They do not have any liquid solution in them. So the answer to the first question is that if you ask us which iron carbon alloys undergo this reaction, it is all cast irons, all iron carbon alloys which have carbon in the range 2.11 to 6.67, which undergo this reaction. Students, the second question with pertaining to this reaction that can be asked is that which of the iron carbon alloys undergoes this reaction completely, or specifically which of the cast irons undergoes this reaction completely. Now we have already discussed in several sessions that what does this completely word mean. Completely word means that the if you look at which is the cast iron which above the eutectic temperature would be containing only that phase that is required for the eutectic reaction, so that after the reaction it contains only that product or product phases which come through the eutectic reaction. We know that for eutectic reaction we need liquid solution, and we also know that the product phase from eutectic reaction is lead burite. So if somebody asks you which of the cast irons will show the eutectic reaction completely, your answer would be an alloy, a cast iron with 4.33 percentage carbon. Now, if you look at the microstructure of this 4.33 percentage carbon cast iron, just above the eutectic temperature of 1147, it only has liquid solution in it of 4.33 percentage carbon, which is the eutectic composition. So that after the reaction, after eutectic temperature, just below the eutectic temperature, if you look into its microstructure, all austenite and all cementite that it contains is eutectic austenite and eutectic austenite. That means it contains 100% lead borate. So this is the eutectic cast iron. Cast irons which are to the left of it or cast irons which are to the right of it also contain liquid solution in them, and that too of eutectic composition at 1147, and that is why they show eutectic reaction. But that's not the only thing present in them. They also contain, see, these cast irons 2.11 to 4.33 along with liquid contain some austenite, and on the right 4.33 to 6.7 also have this liquid, but along with that there is some cementite. Now this liquid, after it undergoes eutectic reaction, will again form austenite, which would be eutectic austenite, and there is austenite already in it. So this austenite, students, would be referred to as pro-eutectic austenite, and this cementite, students, would be referred to as pro-eutectic cementite. So this alloy before the reaction would have 100% liquid solution of eutectic composition, and after the reaction it would have 100% lead borate, means all eutectic austenite and eutectic cementite. But so this is called eutectic cast iron. All cast irons to the left of it would be called hypoeutectic cast irons. Hypoeutectic cast irons just before the eutectic reaction would contain liquid solution in them of eutectic composition and would contain along with them some pro-eutectic austenite. So when the reaction takes place, when they reach 1147, just after the reaction point, just after 1147, this alloy would contain lead borate plus austenite. But how many phases are there in it? See, there would be only two phases. The only difference is that cementite has come only from one source in hypoeutectic cast irons, and that source is eutectic reaction, whereas austenite has come through eutectic reaction also and was there because of the simple solidification also in this range, which is pro-eutectic or primary austenite. So for hypoeutectic cast irons, just after the eutectic reaction, the microstructure consists of lead borate plus pro-eutectic austenite. And for hypereutectic cast irons, just after the eutectic reaction, the microstructure would consist of somewhere over here lead borate plus pro-eutectic cementite. So I hope the eutectic reaction part is absolutely now clear to you. Students, we come to the final and the most important invariant reaction that is shown by the iron carbon systems, and this reaction is called the eutectoid reaction. See, this is the journal form if eutectoid reaction is to occur in any material system, specifically in an iron carbon system. If the iron carbon system is being cooled and it reaches the eutectoid temperature, which is 727, if austenite phase is present, and if it is present, it would always be of 0.77 percentage carbon at 727. So if these two things are present, this phase and this temperature during cooling, the eutectoid reaction would occur, because of which this entire austenite, whatsoever amount was present, will convert into eutectoid ferrite and eutectoid cementite. Ferrite formed would be of the maximum possible carbon, which is 0.02 percentage carbon. Cementite is always of 6.67 percentage carbon, and these would always be formed in a definite weight ratio, which is 1:8. So here you can see which is 8:1. You can see that if exactly 100% austenitic structure is present, then the entire austenite converts to all ferrite and cementite. Ferrite weight comes out to be, amount comes out to be 88.82. Cementite comes out to be 11.18, and that ratio is 8:1. The eutectoid mixture is called pearlite, as I stated earlier, because when you look at this eutectoid mixture under an optical microscope, it gives a very pearly appearance. It appears like a pearl. It shines like a pearl when it has been, when the steel has been etched with a chemical reagent called nitel. Okay, so now let us see again those couple of questions which can be asked. Question number 1: which of the iron carbon alloys will show the eutectoid reaction? The answer would be, sir, any iron carbon alloy which on reaching 727 on cooling, if is containing austenite as a phase, this will undergo the eutectoid reaction. Now students, please observe that any iron carbon alloy, when it reaches 727, will always have austenite phase in it. You look at these steels, it has austenite. You look at these steels and cast irons, they always have austenite. So whenever, except for this iron carbon alloy, which, except for those iron carbon alloys which do not even have 0.02 percentage of carbon in them, and generally such iron carbon alloys are not there, at least 0.06 percentage of carbon is always there in any iron carbon alloy. So but ideally or theoretically speaking, if an iron carbon alloy has this much carbon, 0 to 0.02, then on reaching 727 on cooling, it would have only ferrite in it, no austenite. But practically for all other iron carbon alloys, austenite phase would always be there on reaching 727, and this phase would always be of 0.77 percentage carbon. So virtually all iron carbon alloys, all steels, all cast irons would show to you the eutectoid reaction. So the first questions answer that which iron carbon alloys show the eutectoid reaction. The absolute correct answer is that any iron carbon alloy which has carbon in the range 0.02% till 6.67% will always show the eutectoid reaction. Practically speaking, virtually all steels, all cast irons will definitely show the eutectoid reaction when they reach 727 during cooling or during heating. Now students, the second question, which of the iron carbon alloys undergoes this reaction completely? Now that iron carbon alloy is said to be showing this reaction completely, which just above the 727 degrees centigrade temperature only contains 100% austenite in it. So that after the eutectoid reaction below 727, it contains 100% pearlitic structure in it. Now that condition is met by this 0.77 percentage carbon steel. Just above 727, it has 100% austenite in it, single phase austenite. And just after eutectoid reaction, for that reason only, this 100% austenite will undergo eutectoid reaction, and whatever ferrite and cementite you'll have would be eutectoid ferrite and eutectoid cementite, means you'll have 100% perlite present in this steel. If you look at the steels onto the left of it, they do have austenite, but along with that some ferrite is also there. And this ferrite, students, would be called pro-eutectoid ferrite, because there is another ferrite going to be formed when austenite transforms to perlite. Similarly, all these steels, all the cast irons will have austenite present in them at 727, but that's not the only phase. Along with that, some cementite would also be there, and this cementite would be called pro-eutectoid cementite, because another cementite is going to get formed when this phase austenite transforms via the eutectoid reaction. See, the classification of steels, because it covers all steels, is done by the eutectoid reaction. Cast irons classification already has been done on the basis of eutectic reaction. Eutectic cast iron 4.33 carbon. All cast irons to the left, hypoeutectic cast irons. All cast irons to the right, hypereutectic cast irons. So steel's classification was done though according to the peritectic reaction, but peritectic reaction covered only a small family of the steels having 0.09 to 0.53 percentage carbon. So if you wish to do the classification of steels on a metallurgical basis, it is done on the basis of the eutectoid reaction. So steel which is 0.77 percentage carbon is the eutectoid steel. All steels to the left are hypoeutectoid steels. All steels to the right are hypereutectoid steels. So if you look into the eutectoid steel, just before the eutectoid reaction during cooling, 100% austenite is its microstructure, and just after the eutectoid reaction, 100% perlite is its microstructure. See, any steel or cast iron after the eutectoid temperature will have ferrite and cementite in them. But the question is, perlite is always going to be there, because every iron carbon alloy shows eutectoid reaction. Eutectoid reaction gives you perlite. So every iron carbon alloy is to have perlite phase mixture in it, eutectoid ferrite plus eutectoid cementite. The question is, what what are the other things available? So the other thing is also ferrite and cementite only, but the source of that additional ferrite or additional cementite, whatever you see along with perlite, that is different. For example, if you talk about a hypoeutectoid steel, just before the eutectoid reaction, it has austenite in it, which will form perlite, but it also has ferrite in it, which would be called pro-eutectoid ferrite. So just after the eutectoid reaction, if somebody asks you what is the microstructure of a hypoeutectoid steel, you will say perlite plus some pro-eutectoid ferrite. Similarly, if somebody asks you what is the microstructure of any hypereutectoid steel or even cast iron after the eutectoid reaction, your answer would be, sir, perlite plus some pro-eutectoid ferrite. So I hope students, you have understood this. Very quickly, I'll also show you how does the microstructure of perlite look like. See, we have a lamella of ferrite, and that lamella is 8 times wider as compared to the lamella of cementite. So we have ferrite and cementite as alternate lamella. You have a ferrite lamella, then you have a cementite lamella, then you have a ferrite lamella, then again a cementite lamella, and see, 8 times width, because weight ratio of ferrite is 8 times as compared to cementite in perlitic structure. But that is amount ratio. What we see is the volume ratio, but fortunately the densities of these two phases are the same, so the volume ratio is also 8:1. So you see in a perlitic structure, 8 times the space has been taken up by ferrite, and remaining space has been taken in cementite, and that appears in the both appear in the form of lamella. So to compensate for this amount ratio, the ferrite weight ratio, the ferrite width, the ferrite lamella width is generally 8 times the width of cementite lamella, and because it's a eutectoid mixture, ferrite and cementite are present at alternate lamellas. What I am trying to show through this figure C is that if the resolution of your microscope under which the microstructure is being seen is not very good, because the cementite lamella is very, very thin, if the optical microscope is not of very high resolution, it would not be able to resolve this properly, and these two black lines, the junction of cementite and ferrite, this will not, they will appear to be joint. So what you will see is this is ferrite, which is white in color. Cementite is also white in color because of the poor resolution of your microscope, this thin less width area is not being resolved by the microscope, and it is appearing as black. So you will now label this area as ferrite, but this black line area as cementite. Don't label this as ferrite and this as cementite, right? I hope you have understood. So students, thank you for being with us. In the next session, we'll start with a very, very important and interesting topic that is called heat treatment of steels. Thank you for watching. Thanks for being there.